Hi, my name is Logan Bossert, and I'm a chemistry major here at the University of Charleston. Today, I'd like to talk about the research I conducted alongside my advisor, Dr. Xiaoping Sun, on the analysis of the charge transfer from aromatic compounds to uranyl 6 using UV-Vis and fluorescence spectroscopies. Because this was kind of a lengthy experiment, I decided to skip directly to the results. There were two possible outcomes that we were looking for. These were known as inner sphere versus outer sphere charge transfer. In the case of an inner sphere charge transfer, there is a 90% chance that the electron will reach the uranium center. Electrons flow through a covalent bond, an EDA complex forms, and the resulting absorbance is very strong. In the case of an outer sphere charge transfer, there's only a 10% chance that the electron will reach the uranium center. Electrons will be forced to move through the gap between molecules, no EDA complex can form, and the resulting absorbance is considerably weaker. First were the results of pentamethylbenzene with uranyl. Pentamethylbenzene resulted in a quenching efficiency of 8.694 inverse millimolar. It followed the perfect Stern-Volmer quenching mechanism, which is that the quenching efficiency is linearly dependent on the concentration of the quenching substance, with an intercept of very close to 1. An EDA complex does form, and it follows the inner sphere charge transfer mechanism. First was the UV-Vis spectroscopic analysis of pentamethylbenzene with varying concentrations in uranyl held constant. With each increase in concentration of pentamethylbenzene, there was also an increase in the absorbance of uranyl, proving that an EDA complex forms and that this is via the inner sphere charge transfer. But to solidify these results, we reversed the experiment to keep pentamethylbenzene constant and vary the concentrations of uranyl. The same relationship was observed. With each increase in concentration of uranyl, the absorbance of pentamethylbenzene also increased, proving that it is an EDA complex with the inner sphere charge transfer mechanism. Next was the fluorescence spectroscopic analysis of pentamethylbenzene with uranyl. With each increase in concentration of pentamethylbenzene, the intensity of the fluorescence of uranyl was decreased, meaning that it follows the perfect Stern-Volmer mechanism. Next were the results of benzene with uranyl. Benzene resulted in a quenching efficiency of 0.450 inverse millimolar. No EDA complex formed, and this was via the outer sphere charge transfer mechanism. Upon UV-Vis spectroscopic analysis of benzene with uranyl, no noticeable change in the absorbance of uranyl was observed upon addition of a considerable amount of benzene. This shows that no EDA complex forms, and this is via the outer sphere charge transfer mechanism. We moved on to the fluorescence spectroscopic analysis of benzene with uranyl and noticed that with each increase in the concentration of benzene, there was a decrease in the fluorescence of uranyl, however at a smaller rate. It resulted in the quenching efficiency of 0.4495, which is less than 1, and means that it follows the Stern-Volmer quenching mechanism perfectly, however at a lesser rate. Next were the results of anthracene with uranyl. Anthracene itself had a large intensity reaching almost 400,000 without uranyl. It was a significant progress in research and showed proof that reverse electron demand could happen. A reverse electron demand means that in this situation for the EDA complex, anthracene becomes the acceptor instead of the donor, whereas in normal situations the aromatic compound was the donor. It resulted in a quenching efficiency of 92.5 inverse millimolar, which is very high. An EDA complex forms, and it follows the inner sphere charge transfer mechanism. First was the fluorescence spectroscopic analysis of anthracene and uranyl. As you can see here, the top peak is anthracene by itself with the intensity of almost 400,000. With each increase in concentration of uranyl, there was a decrease in the fluorescence of anthracene. Therefore, it follows the perfect Stern-Volmer mechanism, but with the reverse electron demand theory. Next was the UV-Vis analysis of anthracene with uranyl. With each increase in concentration of uranyl and anthracene held constant, there was also an increase in the absorbance, meaning that an EDA complex did form, and it was via the inner sphere charge transfer. In conclusion, this research project showed that there were definitely a difference between inner sphere and outer sphere charge transfer, as well as possibilities for advancements in uranium chemistry, because uranyl is a strong pollutant in underground water and uranium mines, and using this information, we can precipitate it out to reduce the pollutant.